So we're going to get started with our general methodologies panel. Does anybody know what that means?
Hey, I'm Dave. Ethan's good to meet you.
Raise your hand. What are we talking about? Okay.
I was actually going to switch you guys, but it doesn't matter. It's fine.
So at Nori, our mission is to reverse climate change, and we want to do that by removing carbon dioxide from the atmosphere and storing it permanently. And on this wonderful, diverse panel, we're going to discuss different ways that we can remove carbon dioxide to reverse climate change. And obviously, some of the technologies are more nascent than others. And it'll be moderated by our wonderful Christophe Jospe. Again, as last time, use your name cards to put them up to signify that you have a question and want to ask it. And then I'll come around during the Q&A when Christophe is ready and pass around the mic, and you guys can ask your questions.
Thank you, Alessandra. Okay, sounds like it's working. If all my panelists, make sure you switch it to on and you can see a little green light. So thank you, Alessandra. My name is Christophe Jospe. It's really wonderful to be here with all of you. You could be anywhere in the world, but you chose to be here at Reversapalooza, which is awesome. My role at Nori is Chief Development Officer, but I actually like to call myself a used carbon salesman, because that's my real role. That's really what I'm trying to push onto the world, is we need to buy back carbon that was previously in the atmosphere. And it's a very diverse panel here today. It's called General Methodologies. And what we mean by methodologies are really the methods that go into taking carbon dioxide out of the atmosphere. And my objective for this panel is, by the end of it, we'll have kind of a large landscape view of both the things which can do that today and have been doing that for thousands of years, all the way to ideas which may do a lot of that in the future. And for me personally, it means a lot to be on this panel with Klaus Lackner, who really turned my head inside out and thinking about, whoa, you can remove billions of tons of carbon dioxide from the atmosphere using machines, and then reading David Montgomery's book and saying, well, we can also do this with soil, and it's happening. And I think that the objective of this isn't to say let's compete of what's the best method. I think the Nori philosophy is they're all good and they all have trade-offs and benefits, and without getting too much into the weeds, I'd kind of like to give each one of these distinguished panelists some time to talk about, quote unquote, their carbon removal process, although it's obviously not theirs. It's the one in question. So we're going to start with David Montgomery. David is a geomorphologist at the University of Washington. We all have his bio, so we can see some of the things that he's worked on. What's not noted in his bio is that he's also in a band called Big Dirt. So the next Reversapalooza will have a summit, and then we may end up also having those musically inclined in the room participating in something that's a little more festive. And we need to, because we're trying to reverse climate change, and we can't only be sort of buttoned up and taking ourselves too seriously here. So David, I'd kind of like to just kick it off. And starting with the questions, how does the your carbon removal process work? What are some of the different flavors of the carbon removal process we're even talking about?
Well, it's not a proprietary process. It's not my process. It's one of the oldest processes on Earth, and it basically boils down to photosynthesis. You grab carbon out of the atmosphere through living systems. How do you then keep it out of the atmosphere? And there's only a few ways to do that. One, because once things die, and if they rot and their carbon gets released back to the atmosphere, you've just closed the loop. And if you're trying to actually take stuff out, you've got to park it somewhere. And that can either be in the bodies of living things, whether it's plants or microbes, or in the soil. And one of the things that has become fairly apparent in the last few decades is that one of the big players in keeping carbon in the soil is not so much the decaying organic matter. That's the fuel that feeds the microbes whose dead bodies then become the soil organic matter. There's a new paper, literally another new paper just came out confirming that as well. And if you're really interested in the history of that, go back and read Charles Darwin's last book about worms and how they put organic matter into the soil. It's actually fascinating. I thought it'd be horrible 19th century literature. It's actually amazing. So these ideas are not new. They're one of the world's oldest technologies. It's freely licensable. And how does it work? The soil reservoir for carbon is twice as big as the atmosphere's reservoir. There's a lot of capacity in soils. And something like a third of the CO2 that was added to the atmosphere since the Industrial Revolution came from plowing up the Great Plains, came from degrading soil organic matter in Europe, in Asia, in North America. You look at the amount of organic matter in agricultural soils in the US today, we've lost about half of what we had at the time of European colonization. In other words, there's a lot of freeboard to top that reservoir back up, and we need to think about this carbon in the soil literally as a reservoir, because if you track individual molecules of carbon, a lot of them won't stay there very long. It's a system that cycles. And some will stay for thousands of years. That's why archaeologists use radiocarbon dating to date charcoal. That's carbon that's been in the soil for a long time. But a lot of soil organic matter cycles relatively rapidly. So think of it as a reservoir, like behind a dam, where you've got water flowing in that fills the reservoir, the lake up, and then once you top it up, water bypasses the dam. The soil is very similar, and we need to raise the height of the dam in our soil to get more carbon on average in there and maintain it over time. So if we think about carbon that way as a reservoir, it's a reservoir we could fill up. So what are the practices? I think you're asking, what are the different kinds of flavors?
How do we do it?
Yeah. How do we do it? That's a lot of what I talk about growing a revolution. There's people in this room who know more about this than I do, because they're some of the kinds of people I interviewed. But the two grossest flavors, actually sort of three gross flavors, are cropping, how we do our cropping systems, how we farm, how we raise our livestock, how we integrate the two or not, can all influence how much carbon gets into the ground in terms of cover crops or manure, what are the microbial communities that are associated with that, and how much of their activity gets translated into building soil organic matter. And in terms of the cropping world, I talk about the sort of the coupled system of no-till cover crops and a diversity of crops as the recipe for building soil organic matter. When you go out and you look at the academic literature, what my colleagues tend to look at are one of those things as opposed to the system of all three. So you have to really beware, if you're looking at the carbon sequestration potential of agronomic practices, beware of the studies that just look at no-till, the studies that just look at cover crops, the studies that just look at rotations. I tried to parse those studies in Growing a Revolution, and the few studies I found where people actually looked at all three of those elements, and all the farmers that I visited who had adopted all three of those elements, had dramatic increases in their soil organic matter. Some that were using livestock as part of the mix, whether through intensive rotational grazing or getting livestock back into graze-off cover crops as an alternative means of cover crop termination. But those different kinds of flavors are real. But there's also another one that I didn't write about in that book, but that since we're sitting in the middle of a city, I'll mention. And that's gardening. It's the kind of thing anybody can do. And that we may not be building big carbon markets for that, given the small size of things like the lot that I live on. But we were able to radically transform the carbon content of our urban lot in North Seattle, just a few minutes from here, through gardening practices. The basic principles were identical to what we're working on large farms that are actually scalable and that work in the developing world as well. So it's practices, not products, that can actually really improve soil organic matter in ways that are non-proprietary, readily adaptable. We went from about 1% organic matter to pushing 10% over our yard in North Seattle. And even on a small lot, if you get that down 6 inches to a foot, that adds up to an awful lot of carbon.
That's very impressive. Let's give you a round of applause for 10xing your soil organic matter. Excellent introduction. We'll get back into the weeds a little later in this panel. Our next panelist is Ethan Steinberg. Ethan is a co-founder of Propagate Ventures and leading the business development arm of that. Propagate very much in line with the Buckminster Fuller Institute and kind of how Bucky positions the world is their vision is to make agriculture work for 100% of humanity, which is bold and kind of crazy. And I had the pleasure of meeting Ethan on the subway in New York City, hearing him talk to a colleague of his about planting 1 trillion trees. And I was like, okay, let's get to know each other. And the rest is history. So Ethan is here talking about agroforestry. So tell us, how does agroforestry work? Obviously, it's not the same everywhere. So what are some of the different flavors of agroforestry?
Totally. To go off of the Bucky comment here, one of the things that we talk a lot about in our office is a quote from Bucky, which is, "Don't fight forces, use them." And that's, in a lot of ways, what agroforestry encompasses. So for those who are unfamiliar with agroforestry, I'll give you a quick rundown. It's the integration of tree crops into either livestock or row crop, or in some cases, specialty crop systems. So trees on farms. What we do is we build financial mechanisms to get those trees on farms. The flavors, what they look like, two key ones, and similar to what David mentioned on here, is row crop systems, which would be called alley cropping. So say you have wheat, corn, soy, you're gonna run trees in between those rows. Which will do things like fix nitrogen in the soil, sequester carbon. You'll have things like silvopasture systems. This is where you're adding tree crops to pasture. These will do things like sequester carbon, increase the nutrient value of the forage, increase weight gain on cattle. And then one of the other things that we look at is we look at marginal areas on farms that could otherwise be doing cool things like sequestering carbon or adding nutrient value or adding wildlife corridors back onto farms, increasing biodiversity below ground and above ground. So the reason agroforestry is so powerful is because trees are cool. But why are trees cool and why are we talking about it in the context of carbon? It comes down to essentially trees initiate the carbon cycle in a way, if you will, through their roots, their trunks, and the branches. So the branches and the trunk is the visible form of carbon you see above ground. Below ground, you have a pretty deep, permanent root system. Within that root system, you have something called the liquid carbon pathway. Carbon comes out of the atmosphere, gets through the tree, turns into sugars that nutrients or life below ground consumes and turns into other nutrients, which would help store and cycle carbon in the soil. If you want the science, the guy to my right is the scientist on that one. So those are the flavors of agroforestry, and what we see is the huge gap. How does it get done? What makes it cool, and what makes it something that is actually valuable, and why are we so mission aligned with the folks at Nori? Is that like economics are a core function of making this all happen. For us, we talk a lot about farmer equity and equity in the systems that are happening on farm. If those systems are producing economic value, sequestering carbon, increasing biodiversity, decreasing nutrient runoff, decreasing soil erosion, you're continuing to create the opportunity for the system to have more capacity in terms of storing carbon over time and to cycle that carbon. So to get to Nori's mission of reversing climate change, you're looking at the system as a whole, and trees being integrated into agriculture, which represents about 25% of global greenhouse gas emissions. If we can transition that into something that would sequester something like 4 to 8 tons of carbon per acre per year, start to add those numbers up across millions of acres, that's a lot of carbon sequestered and stored, as well as fixing things like nitrogen and phosphorus runoff that are accelerating climate change problems.
Thank you, Ethan.
Yep.
And Ethan kind of preemptively answered a question that's coming, so I'll invite the rest of the panelists as well, which is talking about we have different ways of pulling carbon dioxide out of the atmosphere, and each one of them presents its own benefit, and you listed quite a few of them, and I think that's a key point here, is that there are co-benefits to doing this activity, and if we look at carbon as kind of the signal, what other great things come along with it? So next up, we're going to have Gregory Dipple. Greg is a professor of geology in the Department of Earth, Ocean, and Atmospheric Sciences at the University of British Columbia. He is also a leader in the field of mineral sequestration, particularly at mines. And I find it a very interesting carbon removal process here, because traditionally mines have been looked at as a very environmentally deleterious activity that are just causes for all sorts of environmental damages. Yet here we have an idea which can reclaim much of this waste material and do something good with it. So, Gregory, same question to you. How does your carbon removal process work? Sort of what are the different flavors, and what are some of the additional benefits that come along with doing it?
Right. Yeah, so I'm a geologist. I normally think about things in terms of millions of years, so I'm not too concerned because I know that weathering will eventually solve the problem that we're all making. It might just take a few million years. But that's also the idea behind the process that we use. So all of our discussions so far have really looked at what we call the short-term carbon cycle. And there's another carbon cycle that operates over millions of years. And it's actually, the reservoirs in it are huge. More than 95% of carbon on Earth actually is in rocks, not in the atmosphere, the oceans, or in living organisms. And, but that cycle operates very slowly. And so we normally decouple the short-term carbon cycle and the long-term carbon cycle, which is more responsible for long-term climate change. One of the main processes in that system is chemical weathering, whereby essentially acid from CO2 from air reacts with rock, which neutralizes that acid and ultimately puts the carbon dioxide into mineral precipitates, which are geologically and thermodynamically stable. And that's why 95+% of carbon on Earth is in that form. What we find in mine tailings is that we take rocks and we increase their reactivity millions of times over by crushing them up and removing ore. And so we take a process that exists in the long-term carbon cycle and we essentially move it to the short-term carbon cycle. And we do it in a way that can provide considerable benefit. We've worked at individual mines that are actually offsetting 12% of their annual total CO2 emissions by accident. And they can double or triple those numbers by changing how they do their mine operations, not by necessarily invoking new technologies or fundamentally new processes. So that's really the arena that we operate in. The process is one where we essentially take carbon dioxide from either air or from a source of CO2, which could be produced from an industrial source or from direct air capture, something that Klaus will talk about in a minute. We then we buffer the acidity in that material by reacting it with ultramafic rocks, which are magnesium silicate rocks, and the end result of that is thermodynamically stable magnesium carbonate minerals, which provide a long-term storage place for CO2, but also provide additional benefits in terms of dust, essentially dust mitigation, encapsulation of toxic metals, stabilizing tailings storage, even potentially building infrastructure like dams and roads. So there's benefits that come in that direction. Some of the different flavors that we look at, so what we find, we started off by doing a lot of field-based studies at mines from around the world. And what we find is that every environment is different. So the processes are controlled by the local climate. They're controlled by the local geology, the nature of the rock that hosts the ore, and they're also controlled by the way that the mines are designed. And so the approach to this is to have a toolbox of techniques that we can use and optimize the approach for the individual site. So again, we're not technology driven specifically. It's really a toolbox approach, understanding the larger picture, the overall set of processes, and from that we can optimize our behavior to maximize the amount of carbon uptake. And it's at the scale of an individual mine, it's important because for the types of mines that we're talking about, they have the capacity to sequester about 10 times more than they emit. So if they can get past about 10% efficiency, they can become a net carbon sink and start to offset local environmental impacts associated with mining. And that, if you take that idea to the extreme, you end up with the idea of essentially mining for the environment. And that might be the way in which we look at trying to do carbon removal in the long term.
Thank you. Excellent introduction. And last but not least is Klaus Lackner. Klaus is the director of the Center for Negative Carbon Emissions at Arizona State University and also a professor at the School of Sustainable Engineering and Built Environment, and one of the pioneers to start looking at carbon removal at the industrial scale. So Klaus, same questions to you. How does direct air capture work? What are some of the different flavors? And what are some of the additional benefits of industrially extracting CO2 from the atmosphere?
Well, in some ways, I'm sitting on the wrong panel, right? I'm not really removing any CO2 because I'll just collect it, right? So the basic idea of the technologies we are looking at is to get in contact with the air and say there are 400 parts per million, which is a low number, but nevertheless, 400 parts per million of CO2 in the air, and we want to get it out. And when I started to think about this some 20 years ago, my first thought was it's too dilute. We can't really make this happen. So I said, maybe we can figure out how dilute is it really. And I know another technology which is very good at pulling things out of the air, and you all know that, that's wind energy, right? And so I said, well, if the value of a kilowatt hour of kinetic energy in the air is, let's say, 5 cents, I can figure out how much value is in a cubic kilometer of air, and it comes out to be $300. I can then say that CO2 needs to be removed, and these good folks at Nori are going to pay eventually, or have a market which pays eventually a tipping fee of the order of $30. Turns out that same cubic kilometer of air contains $21,000 worth of CO2 in it at that comparison. Now, neither the windmill will get all of it out, nor will we. And so the technology question is, how can we do this? So, well, people said, first of all, every tree can do that. So clearly it can be done. Although there are plenty of people who said it can't possibly be done. And I think this is a little bit like in the aviation industry where people said, heavier than air flight? Out of the question. Don't look at that bird outside the window. That doesn't count, right? And I would argue, if you talk capture of CO2 from the air, that tree demonstrates that it can be done. So we are not really competing with the tree. We want to be the airplane, not the bird. And I would argue we will be probably a little more expensive, but we have no scale limits, because an artificial tree standing in the air can actually be about 1,000 times faster at collecting the CO2. So my analogy would be, you can pull a plow with a horse or with a tractor, and eventually the tractor wins. It's not as nice and not as picturesque, but it can in the end do it. So the big question is, can you do it thermodynamically? The answer is yes. Can you do it economically? The jury on that is out. We have argued that the standard argument is just too dilute, and there's the argument, if you look at flue gas, you're 300 times as dilute, therefore you're 300 times as expensive. That's known as Sherwood's rule. We think we can beat that, because the Sherwood's rule really says that first step where you touch the air has to be very, very cheap. So we have said we are passive, like the windmill. We stand in the wind, the leaves of our tree absorb the CO2, then we process them. The competitors, and there are a few out there are some startups who collect CO2 from the air, and they use blowers and fans, but they spend every effort to make those as little and as weak as they possibly can, because they also see the Sherwood rule argument. Our particular sorbent is one that binds CO2 when it's dry and gives it back when it's wet. Other people have a thermal swing. They make it hot in order to get it back off. So there are a handful of technologies. Kleinberg's in Zurich has now reached about a $300 a ton level. That's, of course, way too expensive. I noticed that earlier, said $30 a ton. On the other hand, we are now 100 times cheaper in photovoltaics than you were in the 1960s, and you're about 60 times cheaper on a windmill than you were in the 1960s. So rather than seeing that the glass is half empty, I see this as the glass is half full. We need to mass produce, get on that learning curve, and come down. And I would argue there's another player in this game which is pulling the CO2 out of the ocean water, and I think that is effectively the same story. And we can argue which of the two is better. Thermodynamically, they are equivalent because the two are in equilibrium anyhow. I picked the air because there it's 1 in every 2,500 molecules, that's the CO2. In the ocean, it's 1 in 25,000. On the other hand, you have electrochemistry going for you, which you don't have in the atmosphere. So if you have a good idea on one or the other, I really see them as nearly equivalent. So those are the options. I think the price will come down. Once it's below $100, it gets very interesting. And I would argue, if I look at our particular cost of the raw materials, the stuff we can't get around, that adds up to somewhere between $10 and $20 a ton. So $30 a ton doesn't sound impossible. At that point, that gallon of jet fuel would need a 25-cent surcharge in order to get its CO2 back. And I think it's one of the few things which could promise that in 40 years, we can pull 100 ppm back. For that, you would need 100 million units, which can pull 1 ton a day. These are the size of a trailer truck. And if you could do that, it's big, but it is an industry which is still smaller than the aviation industry. And we build 80 million trucks a year right now, cars and trucks a year. And you would need to build 10 million such units every year if they last 10 years to build up the necessary fleet. So I think we can play a big role. We are the capture guys, we are not the removal guys. And we can talk to the removal people, all of you, including the greenhouses, and we can make fuels out of it in order to close the carbon cycle that way. But ultimately, if you want to come back 100 ppm, you have to put 100 ppm, which is roughly 1,500 billion tons of CO2, somewhere underground. I think the opportunity not to do carbon storage we had in 1980, and we let it go. But now we are at a point where we are too high, and we will have to come back by give or take 1 trillion tons of CO2, and we have to figure out where to put it. Thanks so much.
Excellent. Okay, so I'd like to ask a room survey question. How many people believe, not just these methodologies, but as an aggregate, that there is enough space in the planet to pull back all the excess CO2 that we've put out there? If you think that's true, raise your hand. Okay, this is wonderful. So why the hell are we shooting for a 2-degree limit when it can be a 0-degree limit? And we just need to balance the carbon. And I think that's kind of the point of this panel, is that there are things that we can do today, and there are opportunities to do these things today. So I kind of want to ask each of you, going down the line, what are the opportunities to scale today? And when you talk about opportunities, you have to talk about challenges, because obviously there are hurdles we need to jump over. So as we talk about the opportunities, maybe you can, we know it's not going to be easy. You can tell us the challenges as well.
So you want to go in the same order?
Well, let's change it up. Fine, since you asked. Klaus, we'll start with you then.
What's the difficulty? Well, any technology which says I can right now do it for $300 a ton, and everybody tells you if you are not below 100, it's hopeless. And besides, let's be honest, if you tell me you really wanted carbon, my cheapest source, I hate to tell you that, is either a lump of coal, or if I'm charitable, a little bit of natural gas. So you have to admit up front that we have a problem and that we want to solve it. I don't think it's going to be free. And I think our challenge is, this is not a market where you say, there's billions of dollars to be made in the short term. The venture guy looks at you and says, yeah, sure, there is $1 trillion market sometime in the future, but that's too far out, and it's a regulatory market. So we actually have a lot of challenges there. There are a lot of technical details, and you're going to spend, if you build a new car, you're probably talking, if GM starts with a brand new car, you're probably talking $300 million before they engineered every nut and bolt of that car into the right place, right? If we want to start, we can't spend $300 million, and we don't know yet how the thing actually works. They know exactly how a car works. This is not the first car they built, right? So that's our fundamental challenge. How do we bootstrap ourselves from something which is inherently high cost when it starts to become low cost? And that's why we have to team up with people who do it biologically, because they are already at the low cost.
Great. Greg.
Sure. So we're looking at a process. I don't think the obstacles for us are technological. I think they're practice, just getting more understanding of what happens by trying to moving things from the lab into the field. So we understand there's essentially 3 possible parts of the reaction that can be rate limiting, and the big surprise for us and others was that the rate limits are not the reactivity of the rock; they're actually in the supply of CO2. And we have, I think, some very good progress in the lab in accelerating things in terms of supply of CO2. And so now the next obstacle will be understanding reactivity of rock. And the big learning there is that within an individual deposit, that reactivity varies over orders of magnitude. So we need to be able to focus our efforts on the best rocks. So none of those are technological problems. They're just learning problems. We're working with an industry that invests billions of dollars on decadal timescales, much like the energy industry. And so getting them to change practice is difficult when they're trying to be responsive to their shareholders. So that is in some ways a challenge. I would note we went from having 2 mining companies sponsor our research a dozen years ago to about a decade of none, to now having close to half a dozen that are working with us or are interested. So the landscape has changed a lot in the last couple of years. So that's encouraging. And we will be moving to field trials in active mines, so within the next year or so. So that's all very encouraging. But at the end of the day, though, I have a feeling that it's not going to be the major mining companies that actually do this at a large scale. It's going to be entrepreneurs that come in the middle and lease waste in order to generate value from it. And the last big obstacle for us, I would say, is societal. That if you took all of the mines, this isn't all mines, but the mines that work in the right kind of rock, if you took all of them around the world and generated 100% efficiency, you might do 200 million tons of CO2 a year. That's not really going to change the calculus on the scale of the planet. So for this to actually work in a significant way, we have to actually look at the possibility that you're going to open up new industrial activities, mining, which is generally not looked at in the same way as forests or agriculture, and you're going to have to do it in a way that at a much larger scale if you're going to have a much larger impact.
Thank you. Ethan.
Sure. What's the biggest challenge? I just want to comment on this here. It's 428 tons, not 48. If it was 48, the indigenous communities of the world would win Nobel Prizes for the rest of history. No worries. Yeah, the big challenge, I understand this is a bit of a controversial statement, but the big challenge is people.
All right, we can all go home now.
Mic drop.
Like when it comes to agroforestry, I mean, the science is in it. It generates 140% net income than standard row crop or livestock operations. It increases weight gain in cattle. So that'll crank economic value of livestock. It stabilizes yield. It can lower the cost of fertilizer over time. All the economics are in. Great. Did anyone eat an apple, a banana, an orange this morning? It feeds you. Great. It serves the ecological functions. It sequesters carbon. It restores wildlife habitat. It reduces or retains nutrients in soil, protects watersheds. I mean, the list goes on. So what is the problem? People are the problem. We have this idea that the economics, this and that, need to all make sense. There was a question earlier about the big ag players. Change sucks. And that's part of the reason we're all in the room. It's like this whole concept of climate change is shaking everyone, and that's tough to deal with. So if you're a large agricultural player, how do you deal with something that's going to shake your business for the way your business has operated for the last 50 plus years? It's going to be tough to absorb. So one of our advisors, a guy by the name of Darren Doherty, he runs a group called Gregory, has made a brilliant statement where he says, changing the climate is easy. Changing the climate of the mind is tough. So we can solve all the environmental stuff, but changing people's mindsets is where the challenge lies. So a lot of the work we do is around talking to folks about the economics behind it, because that's where we see the market movers. I know Nori is looking at the same thing. What are the market movers? Back to Bucky, what are the trim tabs that get people to be able to interact with different frameworks that might change their mindsets?
I agree. All right. David, talk to us.
All right, well, Ethan, thank you for setting me up really well.
Yes, you got it.
What I was basically going to say is that the biggest obstacle to change in agriculture is between the ears. It's how we think about the soil, how we think about the land, how we prioritize our practices. And I can say that after interviewing a bunch of farmers around the world who had adopted regenerative practices and documented other real benefits, including bringing soil fertility back to land, which they think about how we're going to feed the world after 2050. And as a geologist, I'm not going to quite go the million-year route, but let's go 1,000 years. You know, it wasn't all that long ago that the Roman Empire crumbled. And I tell the story about how agriculture contributed to that. And it was organic agriculture, just for the record. But the kind of benefits that we can harvest from going to regenerative agriculture are not just sustaining the fertility of the land that we and our descendants will depend on for food, it will reduce our use of things like nitrogen fertilizers, which when we do the calculus for looking at how much carbon we can put back in the ground, don't forget all the diesel and the nitrogen we will not be applying to the land in the future if we restore the fertility of the land. We should include that stuff in the accounting. It's not going to show up in the carbon going into the ground, but it will show up into the carbon or the methane that we don't put into the air. That could be a huge factor as well, which would multiply what we get out of it from a climate perspective. Restoring soils would also help with the global biodiversity problem. You know, a quarter of the world's continental land masses are covered with agricultural land. The future of life on Earth quite literally depends on how we choose to shape the future of farming. Going regeneratively will help bring back not only microbial life that my wife, Anne Baclay, talks about as the biggest unacknowledged conservation project in the world, not just on farms, but within each and every one of us. You know, these things are all, in a way, connected. So what's the biggest obstacle? In my mind, I see it as how we think about the land, how we think about soil, how we prioritize that. Because the kind of things I talk about in the book are practices. Practices have the advantage over products that they can be changed on a dime. They can be changed based on how we think about things. And I've been really impressed at how fast regenerative agricultural practices can actually not only restore fertility to the land, but profitability to farms. The economic angle has to work as well. So it's not just that people aren't thinking right. It's like a lot of people don't know about the potential opportunities to change the nature of how they are dealing with their farm, how they're approaching stuff. Look at who's advising them in terms of their farming practices. There's not a huge market in teaching people how to do things in a way that does not require all the kind of things that people who are generally advising farmers sell to them. Practices are easy to adopt in principle, but they're hard in practice because habits are hard to break. Think about your own lives. I mean, all of us are creatures of habit. So if you think about changing the way you've been farming for a few decades, that's not an easy ask. So we need to have demonstration farms that show it works, so people are not risking their livelihood to go out on a limb and do something they view as risky. We need to figure out how to regionalize adaptations so that we can assist farmers, and we need policies that line up with encouraging adopting practices that cultivate the beneficial life in the soil and that cultivate fertility, build soil organic matter, build soil carbon, but also reduce fossil fuel use and inputs. We need all those things to line up.
Thank you.
And I might have answered the question, but I don't remember what it was.
No, you did. I want to comment on what you're saying. Sort of, we need people who can help those managing the land learn about these practices. I'm so inspired to see many of those individuals actually sitting here in the room and working on demonstration farms or demonstration ideas that just show if we tweak this just a little bit, we can actually create these dramatic impacts. And I think that's wonderful. So I'm going to do two things, just kind of those who have questions, if you want to turn your cards up. I believe one of my colleagues has a mic and will be running around with it. And David, you touched on it a little bit, and it's a question around drivers. What are the things that are going to motivate this particular methodology? And so I'd like to pass this sort of up for grabs to, let's take Nori out of the picture. No one's paying you for carbon removal, but you're going to do this activity anyway. What are the things that are driving this activity? What are the main pulls to do it?
It ain't going to happen if somebody isn't get paid for it.
Right.
So maybe it's a tax break. I mean, keep in mind, right now there's a new budget and a new tax law which basically says if you inject carbon dioxide underground into a saline aquifer, in 7 years from now, this is ramping up, you can get $50 a ton to put it there, provided you did your life cycle analysis and all of that right. So there are starting points where people can, similarly, if I were to feed it into a greenhouse, I could actually get a carbon credit. So people have to start seriously thinking about taking advantage of this. And I think what Nori offers in the story is another way, and I think particularly to pull in volunteers, because if we wait for governments to do that, we are going to be too late. And I don't believe that the volunteers by themselves solve the problem, but they will change the policy debate. And at the end of that, we might actually be able to pay for it, because at some point, I think there will be a regulation, and I would hope for it's as simple as that if you take carbon out of the ground, fossil carbon out of the ground, you have to put an equal amount back. And that surcharge will then motivate to do other things, which avoid taking it out in the first place. But if you didn't, it becomes a waste management problem. You cannot use the atmosphere as a dumping ground for your CO2, and you have to put it back somewhere. But in the end, there may be a service which is paid for, and people tell me, well, I don't have a product if it's a waste. I would point out there are waste management companies, including companies with a name, Waste Management, which make good money on a service, which is to take care of your garbage. And CO2 is one of those garbages, and it's great if it has an additional use. And in a way, I'm motivating that use, because the other end is the tipping fee. And if I have to pay the tipping fee, you can take it as a credit if you can actually do something good with it.
I can comment.
Yeah, if anyone else wants to comment.
Nori aside, agroforestry is going to happen anyways. It's just the reality. Agriculture is in free fall right now. The debt to income ratio is 6-to-1. You have, like, for the last couple of years, you have like a 45% decrease in net income on most farms in the United States. So the numbers are not looking good, and agriculture is falling apart. Luckily, trees, humans' best friend, next to dogs, are kind of right there to support you. And so they make the economic numbers make sense. They solve some of the ecological stuff. So, like, what are the core drivers? I think economics is a huge driver. Like, market potential is definitely there. When we go into conversations with farmers and we talk about transitioning towards agroforestry systems, the conversations are not based around, well, you'll retain 3 times more nitrogen in your soil, which is great. I mean, big benefit. The conversations around you'll increase your net profit year over year by X. So while you want, like, hedgerow to hedgerow of corn, that might have been like the old paradigm model, thanks to a gentleman by the name of Earl Butts. But the new model going forward is actually increasing total capacity of each farm, which will include, like, the soundbite I like to use is diversify your farm for all the same reasons you diversify your portfolio. That seems to resonate well with people.
Yeah, especially in light of what's happening to soybeans now, huh?
Yeah, I would say that the primary motivation for almost all the mining companies that we currently work with is something other than CO2 removal. So I think there are opportunities to develop know-how and experience in doing this, where there's a utilization component where the practitioner sees value. But I don't see that being enough to get us to the large-scale system that we need to get to. So I view that as a stepping stone to getting us to the position where we are doing this for the purposes of carbon removal, and that will require that the cost of carbon be realized.
Yes, I think almost to a person, the farmers that I interviewed for Growing a Revolution started moving into regenerative agriculture out of personal financial difficulty. They faced a financial crisis of not having the money to buy fertilizer one year, or not being able to afford new equipment, and all they had was no-till equipment that somebody else didn't want. What turned me into an optimist in terms of looking at the potential for wider adoption of regenerative agriculture was that after they figured out how to adapt a system to their climate, their soils, their kinds of crops, they were all more profitable than their conventional neighbors because they were using fewer inputs, less diesel, and in the end, growing just as much, if not more. So the financial end, I think, can't be understated, and they all basically indicated that if they were being paid to put carbon back in the ground, that would help motivate their neighbors as well. But there's another dimension to it that almost all the early adopters that I talked with in the regenerative ag movement mentioned, and that is that they recognized the damage to their land that had happened over previous generations. And they really wanted to leave their land in better shape to their grandkids than they got it from. A couple quotes were like, my soil is nowhere near like my grandfather's soil, and I want my grandkids to have my soil. I think we need to, in a sense, couple the economic arguments, which increasingly seem to work for at least in the regenerative ag sector, but couple it with the sort of the ethical, the moral, even dare I say that as a geologist, the spiritual, in terms of wanting to leave the world a better place than we started it. I don't think that that will be an adequate driver at large scale if the economics don't work, but you put those two together and it's a really potent recipe for accelerating change. And we shouldn't forget the other half of it.
Thank you. So we've got a couple of questions. I see one right in front of me. Can't see your name. Brian?
Yeah,
Byron. And
She's got the mic.
All right.
Yeah, I'm Jenna. My question's for David. My background is in geologic storage. So when I look at a reservoir, we look at certain characteristics like porosity and permeability to quantify whether that's going to be a suitable reservoir. So just out of curiosity, I was wondering which soil types are most suitable, and then maybe, I don't know, just give an example of an adaptation for a soil type that's not so suitable.
Oh boy, well I think that, let's see, if you look at nature as the guide, the world's best soils for carbon sequestration are going to be the mollisols, the great grassland soils of the world, in that because they had the highest, other than wetland soils, which are kind of small in area, those would be sort of the big ones. But one of the things that I was intrigued by in interviewing some of the farmers that I talked to is the people who had actually rebuilt their soil organic matter content to greater than the native jungle or the native forest where they lived. In other words, when we think of the reservoir for carbon sequestration in soils, it's very tempting to benchmark it to what the native soil carbon content is. But culturally, we can actually overshoot that. We can do better than that. We've done that in our yard and our vegetable beds that got a lot of biochar and all our worm compost and so forth, and we've got them up to about 15% organic matter, and it's not a wetland. I mean, that's pushing histosol territory. So I think that the challenge would be sort of figuring out how to adapt for different areas. Because if you say you go to the tropics, and the folks I visited in equatorial West Africa, Ghana, they've got their soil back up to about 4 or 5% organic matter, which there is huge in the tropics, because they've been down below 1%. I don't think they'll ever get it a whole lot higher than about 5%. They're just going to be cycling much too fast to actually, but they can hold that reservoir there. And I found wildly varying estimates of sort of what the time frame for topping up soil reservoirs are in different parts of the world. Mostly they've been done for the sort of temperate soils in Europe and North America, for which I think the potential is, the total storage potential is larger than in the tropics. But figuring what that target is and how much higher we can build is something I think will be a challenge. And the idea of biochars, and you asked for an example of sort of an example. Something that might work really well in the tropics is biochar, which is organic matter that's been combusted in a low oxygen environment, sort of turned into charcoal, which can either be pretty inert or have some cation exchange capacity depending on what you make it out of and what temperature you make it at. But that could be a really powerful soil amendment that has a long residence time that could be really good in the tropics. The people I visited in Costa Rica were doing amazing things with biochar that they would inoculate with the mycorrhizal, the fungi and the bacteria out of the native forest, and they're essentially putting together the housing in terms of the biochar for the microbes, adding the microbes, and then brewing up compost tea and inoculating all their fields. How much can those practices build organic matter in the tropics above what nature had done? I think it is yet to be seen.
Thank you. So we've got a couple more questions, so let's try to condense our answers a little more so we can get through everyone. But that was an excellent, it also speaks to what we'll talk about tomorrow, where we go in a bit further depth of how does all this work and how do we know that this is working and measure that this is working. But go ahead, Byron.
Okay.
If that was too long an answer, then I'm thinking I may need to change my question.
No, go for it.
So I've developed solar power plants for about 9 years now, and utility scale stuff. And so that means I've worked with farmers across the country, from California to Maryland. So I've witnessed the fact that the regenerative farming side of this, the soil management, the agroforestry, while those are growing in use, they're currently taking place, and they've had advocates in the U.S. for over a decade plus, right? Those current activities, I sat on a board of a nonprofit in Chicago that worked with farmers to obtain monetization from the carbon markets in the Midwest, and I've worked with soil conservation districts in the state of Maryland to make sure I use cover crops when we're transitioning farms to a dormant use to put solar. So I say all this to tee up the question really for the Nori guys. Your economic unit that will back the currency, you have a lot of different constituents across the country doing a lot of positive things that may be exactly what you're trying to create, or maybe only halfway there, or maybe only 10% there. How are you guys thinking about how you're going to work with them so that you're not just creating another unit, but you're creating something that is synchronized and can push the market forward faster?
That's a really good question, and I'll give you a short answer, and then let's talk after, and I'll give you a longer answer. And let me make sure I get the question right. How is the economic unit we're creating going to incentivize the right behavior in the shortest amount of time? Effective? More or less? Well, so we are aiming to put out the first cryptocurrency which is pegged to the removal of 1 ton of carbon dioxide from the atmosphere. And so no one's done that yet. So our hypothesis that by doing that, will put liquidity into a marketplace so that people who have been doing that activity all along, and certainly starting in the regenerative space makes a lot of sense for so many reasons, because not just on the carbon side, but all this additional benefit which they may accrue. One of the wonderful things about blockchain is as you are verifying certain data that comes through, and it might create certain data layers. And I would actually encourage everyone to read Regen Network's white paper along with ours as well, because they not only point to the drawdown potential when we're looking at farms, but also all of the ecological services which farmers can monetize as well. And so what we're talking about is helping people track and verify these activities, and starting with a building block on the carbon side, and ensuring that that goes directly to people who are doing that activity. So let's look at traditional offset markets. And I know this is getting a little bit away from what this panel is about, but the traditional offset markets take a rather large haircut on what the supplier of that offset is actually doing. So by setting the cryptocurrency as the medium of exchange, what the buyer on one side pays for that and what the supplier gets, it's 1-to-1. And where Nori makes its money is on a small transaction fee up front. So how does this drive more of what we want to see happening? Well, if I'm getting now paid for the carbon removal in my fields, and my neighbor is saying, what are you doing over here? I want to get paid too. We make that as easy as possible to subscribe, and we'll get into the weeds on that tomorrow. So hopefully that answered. I think we had, if you want to pass that to Sean and then David, or who has the mic next? Is Ross? Okay, go for it.
Hello, everyone. Thank you for this excellent presentation and panel. My name is Seth Isken. I'm with Soil for Climate, and I'm holding this Maasai club, which I'm going to refer to as a talking stick today. This was given to me by my colleagues in Kenya, and as some of you know, we're doing a project there on, it's called the Maasai Lands Restoration Project. And the idea of having markets for carbon drawdown for what they're doing is really important, and I'm so happy to be here today. 2 things real quick. First, this pertains maybe to the previous panel, but we need to make sure that really sort of the poorest of the poor, if you will, are participating in being rewarded here, and making sure that the layers of middle people, you know, we're not just selling futures on Wall Street, right? But there's, you know, the people who are actually pushing the cattle around in the rural areas of Kenya are being rewarded somehow. That's really important. Try to keep that in mind. And hopefully we can talk about that maybe more tomorrow. The second question for David and others is, if you're doing a type of regenerative grasslands management, which these people are, what's the sense of permanence, right? I mean, a ton over so many years, you might get a ton, but it literally could disappear tomorrow, right? I mean, a corrupt politician comes in and says, oh, I want to put a casino there, right? And just digs it up, or says, oh, let's plant maize. And then it's gone, it's gone. So I'm curious about the question of permanence as well. And then even if you're managing just to sustain it, even if it's not necessarily increasing, but you're just sustaining what's there. So those are the kind of questions I have. Thank you.
Thank you, sir.
Well, nothing is permanent. As a geologist, I can say that with confidence. That, I think, is one of the really big issues in terms of looking at soil carbon sequestration, is it's very undoable. And if you doubt that, read my dirt book from 10 years ago. That was my comment earlier about how organic agriculture helped destroy Rome, was because if we plow up soils that are rich in carbon, we're releasing that carbon to the atmosphere. And so if we go on a regenerative agriculture kick for 100 years and then plow it all up in 100 years, we've undone all that. So that's a very big issue and a very big question. A geologist may be the wrong person to give you the solution for it, but I think it's in that solution lies in the human dimension. It's managing our own actions. It's in the political, the legal, the regulatory, and the ethical arenas. And that's why I'm such a big fan of arguing that the foundation for that kind of change in that sector, which will help with climate, is thinking about the soil and thinking about the land differently. Because if we think about it, we can structure institutions, we can structure structure deals, we can structure how we treat the land, possibly with, what are those, things when you pay your neighbor to use their land, easements, thank you. Those kinds of things, but the answers to that question are not in the technical world, they're in the human world.
I'll give you an answer today which is very different than what I would have said a decade ago. A decade ago, I would have said it better be permanent because we need to level out and we need to balance the budget. I think it's not so much that I changed, but the situation changed. We are now in an overshoot. And so as a result, we have to bend the curve down. So if you give me a 10 or 20 year storage, I actually think that's important to have. We can then figure out in 20 years from now what to do again. And so I would actually urge you to think of this. I would like to see a certificate of removal which inherently is considered permanent, but I would also say what you actually purchase is a rental agreement that for the next 10 years you have the carbon here, and if you keep your soil going, you can come back in 10 years and rent it for a second 10 years and a third 10 years. But don't assume right now that we actually know how to do that. Now on the buyer side, I am driving my car, I would love to push that button on the pump and say, my CO2 is gone. I implicitly think of this as being forever. So I effectively pay the rent for an infinite sequence of 10 years, and people who do net present value can calculate this for you, and they will get actually a finite number. And so I'll pay maybe twice as much as you get for the 10 years. But that also solves your problem that you can't have these farmers not get anything for it for decades and decades in a row because they locked it up in 2018 and now it's 2090 and they are still obligated to hold this in place. So you think of it as a big warehouse and you rent space in that warehouse where you are storing your carbon. And I think it gets a lot easier to think about the problem.
And the permanence question is one that keeps many of us up at night at Nori, if not all of us, and it's something that Klaus's comment is a comment that I believe will be reflected in our white paper of how we think we can deal with that issue. How are we on time? Because I think we're supposed to end.
5.
We'll go 5 more minutes.
Outer space.
So we had 2 questions up front here. Ross, were you going to ask a question?
No, I can come up front.
Two questions.
I've been in the back most of the time.
Yeah, these two have been patiently waiting, and then we'll let you all get some lunch. Where?
Sorry. No worries.
I'm hearing that regenerative agriculture increases profit. So my question is, does it increase profit by decreasing cost or by increasing output? Maybe both. But is it possible that cross-subsidizing food with carbon credits would decrease food prices and harm farm profit in the long term?
The answer is both. It does both of those things. That's a tough question to answer, to be honest.
Is low prices the reason for 6-to-1 debt to income that you were talking about?
Yeah, like the policy is a problem.
Or is it high costs?
It's
Too much fertilizer?
it's both. What we did is after the Second World War, we transitioned into a style of agriculture that focused on specialization in crops. So we separated livestock from animal husbandry, and farmers specialized in growing 1 or 2 major crops. And they became so good at doing that that the per unit price they get for their harvest is actually quite low. But they've also increasingly were taught to rely on methods the cost for which have gone through the roof in the last 80 years. Diesel, fertilizer, patented seeds, pesticides. So basically, the farmers have been caught in the squeeze in the middle between those two pressures. And then the advice to get bigger, big out, or get out and all the overcapitalization problem. But what I saw as a major short-term economic advantage of going regenerative was the greatly reduced input costs. Because if you're thinking as a farmer, and you don't basically get to set the price of fertilizer, and you don't get to set the price on the other end that you get for your harvest. You're kind of at the mercy of other people's, other bigger forces than you can manage on your farm. What you can do on your farm is adjust your practices. So what I saw as enthusiasm would be if you can go in and talk to people about how by rebuilding the health and fertility of your soil, you can reduce your fertilizer cost. And you can maybe cut your diesel bill in half because you're not plowing, and so you're taking half the trips across the field. Those are very real and direct incentives for short-term change. A number of the farms I visited had a dip in productivity for a couple years after they started the transition. But I was amazed at how short that dip was and how short the time scale to better profitability was. Because even if yields dropped a bit, if you take a field that's been on nitrogen for 100 years and all of a sudden you take it off, you got to build the organic matter back up before you're going to get the same yield. But it can happen actually surprisingly fast with the right methods. So I don't even recall the second half of your question, but it's the big impact that I saw was reduced input costs. Some farmers had much higher yields, but the pattern that I wrote about in Growing Revolution was that there was not a big long-term dip in yields.
There's also a quality over quantity component to this. With regenerative practices, part of the outcome is higher quality produce. Whether that's wheat, whether those are apples, doesn't matter. Higher nutrient density, higher quality, healthier to eat. Which, when you look at what's going on in the grocery stores on the shelf, that means premium pricing. And any farmer can get behind premium pricing. Yeah.
One more question, because I've been looking at Greg, and I feel bad that he's in the front and getting ignored. And then we're going to wrap up.
Thanks. Okay, so my question is, if we think about scaling all of these different, some of them are technologies, some of them are techniques or bundles of practices, transformational practices. If we think about scaling each of these to the economy of scale that's necessary to be effective in having an influence on significant levels of atmospheric carbon, what are the other downstream effects in our world, in our economy, in the daily life of people who aren't directly related to each of these different technologies? And just kind of like holding that, beyond the single sort of reductionist economic measurement of how much money does it cost to achieve that unit of carbon drawdown? What are the other benefits, costs, and downstream effects of each of these? And that's too big of a question to necessarily, answer in full. And mostly I'm asking it so that we're all kind of thinking about that. And I'm definitely interested in hearing what the panelists are thinking about that as well.
Let's go down the line. That's an excellent question.
Yeah,
a good closer.
It's a great question to close because the thing that I see in terms of the downstream effect that could affect society broadly, not talking about the farmers, is that if we were to reform our agricultural system such that it was dominantly regenerative and we restored the health and fertility of our land, and if the nutrient density of the food that we were growing on it was higher, for which, frankly, we need more data, but the science behind it makes sense. If we grew a more diversified set of crops, which is that third principle of conservation agriculture, and we ate them, and didn't feed them to cars or cattle, we actually consumed them ourselves, that's a recipe for actually building a healthier population. The potential connections between public health and style of agriculture deserve a lot more attention. And I think there's actually a huge potential for reforming our agricultural enterprise, our global agricultural enterprise, to echo in improved human health in terms of eating more nutrient-rich foods, in terms of eating more phytochemical-dense foods, the kind of things that we might think of as preventive medicine, and shifting our diets into line with that is one of the biggest levers on public health that we could have. So I think there's a huge potential, but it's very abstract at this point.
I have an easy way to make that make sense. Who in the room is gluten-free? You might want to check your allergy to agrochemicals and not gluten. Not to say, I eat gluten-free too. Rice is great stuff. The short answer is a healthier human population, revitalizing the middle class, which means like a stronger economy. I mean, you want to get into the conversation of what a stronger economy looks like, talk about like increasing peace and conflict resolution. You're looking at decreases in all sorts of things that we would otherwise consider terrible, like war, for example. So how deep down this rabbit hole do you want to go? There's a lot to think about.
If you are trying to come back 100 ppm, maybe while you're still going up, but you're pulling the equivalent of 100 ppm back, you want to do that in 40 years, you need a negative emission industry, whichever way it works, on the order of current emissions, because we are on that. We are going up 2.5 ppm a year. If you were to suck equally hard on the air, you would come down 2.5 ppm a year. So that scale, you would need the equivalent of 100 million shipping containers. You could do that downwind of them. You would see air which looks like it did in 1800 because you took something out. I don't think you would see a direct environmental impact except you built that industry. You would have to store the carbon. I think if you go, one of the nice features of air capture is you can do it in remote locations. You could be in the middle of Australia. Wherever you find good geological formations, you could inject. And so you can hide that to a large extent. So your footprint would be relatively small. What you would see on top of it is a big economic activity comparable to today's aviation industry, of which would create jobs and efforts. And I would argue the last big potential benefit is I see right now solar energy, particularly photovoltaic energy, running down the learning curve at a very, very fast rate and is starting to undercut very seriously fossil energy. And that is, I think, an enormous, we are at a tipping point there. And the big issue is it's horribly intermittent. There's a mismatch between summer and winter. And while you can deal with 10-minute mismatches easily with batteries, or even a few hours, if you asked about the capital investment in batteries which sit around for a year, to transfer things from one winter to summer or the other way around, you cannot afford it. So here we have an enormous potential. Whenever you have too much power, make hydrogen. Then take the CO2 we give you and make a liquid fuel. Maybe methanol, maybe jet fuel. Most of it you will store in order to give back at the time you didn't have electricity from sunshine or not enough. And what's left over is driving the transportation sector wherever you cannot make it electric. And I would argue heavy trucks, ships, and aviation are essentially out of this. So you can build a very, very large industry, which is bigger than the oil industry and smaller than the aviation industry, if you want to bracket it, around these kind of scenarios. And I see no fundamental reason why these kind of technologies couldn't reach full scale. And I think that's why they complement nicely the others. If you just fill up, clearly you didn't take care of the fossil fuel if you went twice or three times as much. But here you now have an opportunity. You basically scale is, that's the reason I'm interested in it. You can scale it with a very small footprint.
For mining, I guess the two big costs are a carbon tax and land use. And so you have to decide, I think we have to decide if, what does that carbon cost mean for the average person? And then do we need to make the decision if we're going to use, essentially disturb more land in the task of mining. Obviously, typically in remote locations, but it's land disturbance nonetheless. The footprint is about maybe 1/10 to 1/100th of photosynthesis, so it's a smaller footprint, but you're still disturbing the land and doing things. So you need to find out if, we need to determine as a society if it makes sense. I'm not advocating mining for mitigating climate change, but I think we need to figure out the answer as to whether or not we should be doing that long term. The cost for carbon, we can do a lot right now. In fact, some of the back of the envelope calculations that we've done suggest that we can get to the gigaton scale at $30 or $40 a ton CO2. I pay $35 Canadian per ton right now in British Columbia, and that'll be 50 going up $5 per year. So, or I'm already paying that at the gas pump, and it hasn't ruined our society. We have, by and large, hydroelectric electricity, so that helps reduce the impact on people. But that cost hasn't had a huge, the change in the price of gas at the pump, the variability in that and the evolution of that has been much greater due to market forces than it has been due to carbon tax. So I don't think the carbon tax issue is as dire and horrible as it needs to be. We need to figure out the land use issue and figure out if this is a good way to use our land. The benefits are jobs, reducing the CO2 emissions, and we also, would end up producing some of the metals like cobalt that you need to make batteries that you might want to use in the renewable economy. Sorry.
Thank you. No.
To put a number on it, $30 a ton of CO2 is 25 cents on the gallon.
I'm feeling very optimistic after this panel. It's excellent. It's a good way to go into lunch. Before I pass it off to Alessandra, I want to thank all the panelists. I'd also like to let people know that David Montgomery was kind enough to bring some of his books, Growing a Revolution. Indeed, there's a revolution afoot, and so if you are looking for a signed copy, he'll be right outside with some of those books. So let's give our panelists a round of applause.